Okay, so we got to the last talk of this meeting. Probably it's a good opportunity to thanks to the organizers, to Mathematical Sciences Institute, especially to the director, to you and to Ted. It's my great pleasure to be here again. And I hope everybody enjoyed here. Okay, so let us get to the talk. Hope also that I would not disappoint you. In this last talk of this meeting, I would like to present some recent results. They're kind of partial ones, but anyway, probably it would have some interest. Well, the title is Extending Filters to the Ultrafilters, but basically we will be a bit more modest. What we would like to do, we would like to consider the following. Let F be a kappa complete filter over regular around kappa countable. Can it be a kappa complete filter over regular? Okay, can F be extended to kappa complete ultrafilter instead of over set of size kappa. Okay, so this is kind of big form, very big form of strong compactness, and in such situation, if this is possible, the kernel kappa is called kappa compact. Kappa is called kappa compact if this is possible for every F is above. I believe this notion is due to Tarski. Okay, so the question is how strong this property is, and there were results by Mitchell. He shows that at least O kappa should be kappa double plus. Then I was able to show that there is in a model there is a strong cardinal, and quite recently Yair Hayut produced a couple very, very interesting results concerning this cardinal. He was able to show the following. He showed that if kappa is kappa compact, then square kappa plus square with brackets kappa plus breaks down, and this is already quite strong due to the fact that kappa is measurable, so also square brackets kappa breaks down. And by results of Jensen, Schimmerling, Schindler, Steele. This implies that there is in a model with class many Boudin cardinals, class many strong cardinals. Also, if we have a mouse that iterable, but there is a result by Neyman and Steele, which says that under something like this, if we have iterable mouse that computes kappa plus correctly, then then kappa is pi 1 subcompact cardinal, and let me state what it means. The meaning is like this, that for every A subset of H kappa plus, and for every sorry? Yeah, in the mouse, yeah. But let me state the definition, pi 1 subcompact, just V. For every pi 1 statement, phi, such that the structure H kappa plus epsilon A models phi there are some rho less than kappa and B subset of H rho plus, and such that H rho plus epsilon B as far as phi, and there is J elementary embedding from H rho plus epsilon B to H kappa plus epsilon A. Critical point is rho, and J of rho is kappa. Okay, the difference between the subcompact cardinal is just this addition, that we have pi1 statements that we would like to reflect down as well. Okay. Well, and what Yair Hayut pointed out is that actually, if we have such a cardinal, if kappa is pi1 subcompact, then it's actually kappa compact. And he conjectured that actually it should be the exact strength of kappa being kappa compact. It should be this pi1. Sorry? Yeah, I think so, yeah. Thank you. If kappa is 5 and 2 to the kappa plus. Yeah. Okay, so this is the picture that we have now in general, and so the conjecture is that this is the correct strength. So the evidence points in this direction. Well, another very nice result by Hayut is like this, and it relates actually more to the topic that we would like to concentrate on. Look. Let us try to relax a thing. Instead of extending every kappa complete filter, let us make it a bit, let us narrow this a bit. So I asked once a question, what happens if instead of looking at any kappa complete filter, let us try to extend only normal one. Okay? And what Hayut showed that if every normal filter over kappa can be extended to a kappa complete ultrafilter, then kappa is kappa compact. So it's just the same. Okay. Well, now what I'm trying to talk about is further narrowing of this general setting, and the results I'm going to present are joint with Tom and Hamo, Yair Hayut, me. What we are looking at is the following setting. Suppose we have now a forcing notion. Let Q less than equal be a kappa distributive forcing notion, let's call it, poset of size kappa. Then look at the dense open subsets of this Q. They naturally form a kappa complete filter on Q. Q is of size kappa, so it's just can be transferred to kappa if one likes. So let us consider F, call it FQ, be the set of all D subset of Q. D is a dense open. Okay. So this filter kappa complete filter over a set size kappa, and let us ask if when it is possible extend it to an ultrafilter, kappa complete ultrafilter. Well, it turns out that this question is closely related to the following. Can Q be embedded into Prickly type forcing? Actually, theorem more or less, let me simplify the thing. So FQ can be extended to kappa complete ultrafilter if and only if Q is subforcing of the prickly, basically three forcing. So it's a little bit simple. The real result is a bit more complicated. This one relates for homogeneous Qs because taking different elements of Q give rise to different filters, and if Q is homogeneous, then it's easy to formulate. The basic idea is here. Well, look, there is here additional thing. It's maybe interesting by itself because in contrast to the prickly type forcing, there is no nice way of iterating distributive forcing notion. And if one can embed distributive forcing into prickly type, then it allows the possibility just nicely iterated. So now let us address the subject. What large cardinals do we need for this type of thing? So let us only state one more old result. Look, if we consider the pre-creep forcing with a normal ultrafilter, that's the usual one, basic pre-creep forcing. Let U be normal filter over kappa, PU, the pre-creep forcing. With U. One can ask what are the subforcing of this forcing notion, and turns out the answer is kind of disappointing. It's resolved by Novay, Kopke, myself, that every forcing of PU is trivial or PU itself. So there is no hope if we deal with normal ultrafilter to find some non-trivial distributive forcing notion inside. But the situation changed drastically if we turn to non-normal ultrafilters. Okay? And for non-normal ultrafilters, the following, for example, let us look simplest probably forcing of this type. Let us look Cohen forcing for adding a subset of kappa. Okay? Cohen kappa. So let it be our Q. And for this one, suppose we would like to proceed to deal with the same problem. We would like to consider filter of dense open subsets of Q, and we would like to extend it to the kappa complete ultrafilter. What do we need for this? What is the strength of this? And it turns out that actually one measurable is enough. So starting is a measurable kappa. Is it possible to force kernel preserving extension where this we need to take second ultra power. No, you cannot just get out with one single ultra power. I don't think so. You need two ultra powers, then you can. Because of this. So anyway, one measurable so let me okay, and once we have the thing for Cohen forcing, then we have plenty of others. For example, adding a Suslin tree to kappa, adding non-reflecting stationary subset of kappa, whatever. And it's possible just to give a general setting for this, but let us continue. So this is from one measurable. Now, on the other hand, if we would like to deal with any kappa distributive poset of size kappa, then something similar to the result of Hayut from pi11 subcompact would work. But instead of allowing parameters in subcompactness, we can do with a light phase version of subcompactness. So gives a positive. For any such Q. Such, I mean, kappa distributive poset of size kappa. Now, and again, our conjecture would be that this is the exact strength, and it is strictly below pi11 subcompact. Okay, let us try to restrict a little bit more. Let us try to deal instead of just kappa distributive. Let us look at less than kappa strategically close forcing notion. So suppose Q is less than kappa strategically closed forcing notion. Well, for this one, it turns out that a weaker assumption can be used than subcompactness. Let us, okay, so the result would be like this. Theorem. What we are going to use a version of super strongness with the target of sufficiently large cofinality. So suppose that there is J from V to M, critical J is kappa, and suppose that J of kappa, 2 to the kappa J of kappa, is subset of M. Okay? So if cofinality of J kappa is bigger than 2 to the kappa, it just follow. Okay, then FQ can be extended to a kappa complete ultrafilter for every less than kappa strategically closed was it Q of size kappa. And let me show a simple argument. Let me just show you the proof. Okay, so without loss of generality, we can assume that Q is just kappa itself. Denote 2 to the kappa by lambda. And now let us use strategic closure. Let us move to M. So Q was strategically less than kappa, strategically closed in V. So J of Q or J of kappa would be J of Q is basically J of kappa is less J of kappa strategically closed in M. And pick the strategy for the good player, second player, and let us play a game here. Before it, let us fix in V enumeration of all dense open subsets of Q. So let the alpha less than lambda be a list in V of all dense open subsets of Q. Well, so fix in M strategy sigma for good player and let us proceed as follows. Just we have two players, so 1 and 2. By good, I mean 2. He plays at even stages. As the first stage, let us pick just any condition, P1. Then, at the second stage, we will take a stronger condition which belongs to D0. Then, sorry. Let P0 belongs to, no, let P0 be just, as I started. P1, then take P0 to be just any element of D0. Then play according to strategy. Let P1 would be the answer by strategy to P0. Then, which is above, stronger than P0. Then we continue. Let next step would be Yeah. I mean, we would like to build increasing sequence. We would like to build a sequence of condition one strengthening of another, and eventually we would like to pick an element from every dense set from the list. No, we are working in M. And note that what happens at limit stages. Yeah, it would be J, sorry. J D0, J D1, that's it. At limit stages, we are fine because because M is closed under, we have such a closure. So we have a sequence in M, and playing according to the strategy, we can extend it. And so we can proceed all the way. And the final thing, so say we play game lambda many stages, and know that lambda, which is 2 to the kappa, it must be less. So what we are doing, we constructing the sequence P alpha less or equal than lambda. Lambda is less than J kappa, because of this assumption, lambda is 2 to the kappa. So we can proceed and look at the final thing, P lambda. And now what we have, P lambda belongs to J of d alpha for all alpha less than lambda. And let us use it to define ultrafilter. So let us call it F star Q, this set of all x's, subsets of kappa, such that P lambda belongs to J of x. So it's ultrafilter, kappa complete, and it extends the original one, FQ. Because of this, we have this property, and we have the list of all the sets. So we are done. Okay? Now we have an upper bound, which is at the level of super strong. And we can try to say something from below as well. So a typical forcing would be like this. Let us consider now one particular forcing. Let us consider Q, which is set of all A subset of kappa. A is of size less than kappa. A is closed, and A avoids accessibles. Okay, let Q be ordered by an extension. So the forcing notion Q is desired just to add a club that runs away from every inaccessible below kappa. And this forcing notion is of this type. Q is less than kappa, strategically closed. And in a sense, this one turns to be typical. What can be done? It is possible to find in this class of less than kappa strategically closed forcing notion of size kappa, it is possible to find a universal one. The universal one is of this type. And let me not go into precise definition. It actually considers the forcing for adding square, global square up to kappa. So just by initial segments. And what we would like to add, we would like to add a club that avoids all the inaccessibles, and at each point in this club, we would like, for each alpha in this club, we would like C alpha to be closed and bounded in alpha of order type less than alpha. And we would like coherency. It's called Jensen square. And it turns out that this forcing is actually universal in the sense that every other forcing of this type can be embedded into it. Okay. So what can we say about the strength of possibility of extension of the filter of dense open set for this forcing to the ultrafilter? It turns out that if this is possible, then the strength is, it was our first try actually. It's O kappa should be bigger than kappa plus kappa. And what we thought that it's possible to show the other direction, that it is also sufficient. But unfortunately, it was not the case. And if you look carefully at this assumption, it has actually to do with, it's actually quite close to what we like. If you would like to construct a generic object in certain iterator to ultra power, this turns to be quite reasonable. But unfortunately, it was not the case. He managed to show that it should be at least kappa plus, and it looks it goes up quite much higher. Let me mention one more thing, that another forcing notion which is very similar to this one, but existence of ultrafilter, kappa complete ultrafilter for FQ is much weaker. Let us consider the following: Q prime, let it be the set of all A, subset of kappa, size of A less than kappa, A is closed, and A avoids malo. Cardinals. Okay. So we allow inaccessibles, but not malo. For this one, it turns out that measurable is enough. I have time, so let me probably sketch what is going on here. So look, suppose we're in a situation that we have this nice ultrafilters that extends FQ. Take ultra power, and let us look what happens there. So suppose we have F, which extends FQ, and let us take ultra power, so JF from V into, and F is just power V by F. So f is basically like this, x times q identity function belongs jf of x. Now look at this identity function. Suppose in situations there is no Wooden cardinals or whatever, then we can just analyze this embedding JF. So it is iterated ultra power by measures of extenders from the core model. Suppose we have core model here. Call it K, and we consider, say, J just restriction of the core model. So this J in general, by the result of Ralph, it is iterated ultra power. And look at this one. Suppose Q is kappa, for example, right? Just the same. So identity would be an ordinal. So we have interval. Let me just draw the picture. We have interval kappa, J kappa, and we have here this ordinal identity. Now look, it should be singular, because it is a point typically in all these sets that exclude inaccessible. So if it is singular, it is possible to argue that we have this iteration ultra power and kappa moves, say, look at trace of kappa before reaching J kappa in this iterated ultra power. It is possible to argue that this one should be one of kappa alphas. Say kappa, then we'll have kappa 1, kappa 2, and so on, kappa alpha, and finally we will reach the final stage, J kappa. So this one should be one of kappa alphas. And this kappa alpha should be singular cardinal. On the other hand, the ultra power is just ultra power by kappa complete ultrafilter. So it is closed under kappa sequences. Then let us ask, what is the cofinality? It is singular cardinal in M, F, but it should be regular in the core model of KF. So it should change cofinality. Okay? And if it changes cofinality, it cannot change cofinality to something too small. Its cofinality cannot fall below kappa because MF is closed under kappa sequences. So cofinality of kappa alpha should be at least kappa plus. And now the tempting thing to do is just to somehow to create generic Magidor forcing for this iteration that changes cofinality to kappa plus. The problem is that, well, that we added, the forcing adds a club in kappa. So conditions, the typical conditions should be somehow look like this. It has a bounded part below kappa, and then it has some stuff above kappa, and eventually it hits to this point. So the problematic thing is what happens in these intervals, kappa alpha plus 1, for alphas that lead us to, let me call this one kappa alpha star. So for alphas below alpha star, we have all this interval between critical point, between images of kappa. And we need to understand what happens inside. We have a certain condition that generates this ID, I know, called A star. And we have this A star closed set intersected with these intervals. And we need to understand this intersection. And this analysis of this intersection, it's possible to argue that A star intersected with kappa alphas should be actually kappa alpha for alpha, which is singular already. And actually it allows us to reconstruct inside this model MF, which don't know the sequences of kappa alpha, reconstruct the sequence. And having this sequence, we take it back to V and argue that it's kind of impossible. It's too short one. Okay, this is basically the idea, and eventually we can get here. Okay, so this about distributive forcing notion. Another interesting candidate that can be here is the forcing of adding a club into a stationary set. So in order it to be less than kappa distributive, we need some assumption on this stationary set, and the reasonable assumption is requirements is that a stationary set that we are dealing with is a fast stationary set. So let us look at this. Let S subset of kappa be a fat stationary set. It means that, for every C subset of kappa, club S is exactly C contains closed subsets of any length less than kappa. And if we have such a stationary set, there is a natural forcing, call it club S, that adds a club through S, so all A subsets of S, A of size less than kappa, A closed, okay, ordered by end extension. And this forcing again is kappa distributive of size kappa. Now, what is the strength of the statement that a filter of dense open subsets of this poset can be extended to kappa complete ultrafilter? Well, here we don't know much, but what we can show is that we can give example of particular fat stationary subsets of kappa, which only one measurable is enough for doing this. Okay? The way of getting this, for example, force a Cohen subset to kappa and look for pre-image for every point in the, say, let f be a Cohen function from kappa to kappa, and for every delta less then kappa look the preimage of delta. So for many, it would generate such a set for every delta. And it turns out that under one measurable, it's possible just to extend the filter to such filter to kappa complete ultrafilter. But in general, we don't know, and I think that it's probably possible to produce complicated phase stationary sets that would push it all the way up to this light phase pi by 1 subcompact. Okay, thank you very much.
So you have this embedding theorem, which says that your extension plot is equivalent to embedding
into precrete. Yeah. For example, what I stated for homogeneous.
So when you say pre-precrete, this is the kind with lots of different.
You need a split above after you pick element of Q. Actually, your filter changed.
Right.
You're looking only extensions, only strengthening of this condition. So the filter changed. But you can, if it is homogeneous, you can get out with one single ultrafilter. But you need a version of non-normal precrete forcing with non-normal ultrafilter. Just the same definition like precrete, but you need to allow the next stage to be above projection to the normal measure of this filter. That's it.